Welcome everyone. My name is Elshinawy and I'm here to introduce regression model for solar radiation prediction. So generating electricity can be a costly process, particularly when it involves starting up generators. However, it is possible to minimize these costs by accurately predicting the power a utility will need to produce. One potential solution is to utilize the wealth of data available on solar production and forecasted weather data to create a schedule for solar power production. This schedule would allow utilities to optimize their generator schedules and power rates, ultimately reducing costs for producers and consumers. By combining weather history, forecasting, and information about solar production utilities, we can better understand how much power they will need to produce. So we can create a more reliable and efficient system that benefits all parties involved by utilizing advanced regression models and integrating them with weather forecasting. And that's what we're going to be doing in this paper. So the main organization of the paper is stating the problem, showing some of the summary of our related work, details of the experiments that we conducted, some exploration of hyperbarometer tuning for the algorithms and their effect, finally presenting the final results and concluding, and also having some lines for future work. So the main problem objective is that we want to identify the most effective and efficient method for predicting the solar radiation based on weather data. And that's going to happen by using different regression models. So we're going to be using different regression models. The main purpose is to minimize the error and increase the accuracy in predicting power production. This should result in a significant cost reduction and increased efficiency in the electrical power industry once it's reached out. So these are the different regression models that we are going to be using. Support vector regression, random forest, linear regression, decision tree regression, Bayesian ridge regression, and neural network multi-layer perception regression, and also convolutional neural network. For our data, we used data that is installed. We have installed our weather station on the roof of our building for NMSU, for our university. The weather station records the data and send it to the ambient weather website. And we used two different versions of the data that were available at that time we conducted the research due to an update that has been made to the ambient weather website. So we had an older version that contains 19 attributes, and it covers like from November 2019 to September 2020 with like 71,000 almost attributes or instance, sorry. And also we had other data that like the second version of the data was having 22 attributes, and this is when they updated their ambient weather. They started to use 22 attributes instead of 19, and this was a very small set of data that only included like 771 instances. So we took those two set of data, and data processing starts by removing the instance with unknown values. And we combined the two versions of the data with different headers, and that was a very crucial step to do. After cleaning the data, we were able to have 17 attributes in both, and the number of instances, of course, for the first data was much less than 68,000 instead of the 71,000. But we were able to reduce it to only 17 attributes that are combined between the two data, and we got them as our data that has been used for processing. The main attributes for those that we have been using, those 17 attributes are shown here. It's like the date, the outdoor temperature, the wind gust, monthly rain, humidity, relative pressure, and so on. So these are the different attributes that we have been used. And it's also good to mention that we standardize those features using the scikit-learn standardization function on the data shape of 68,000 attribute instances with 17 attributes. So in order to evaluate the performance of various machine learning models, we employed a standard splitting technique where we have 70% of the total data set was randomly selected for training. And at the same time, the remaining 30% were reserved for testing. This allowed us to train our models on a sufficiently large portion of the available data and assess their generalization ability on previously unseen data. Using this approach, we could test the effectiveness of various algorithms and compare their respective performances under constant conditions. So let's start with the first test or the first model that we used was the random forest regression. And it's good to know that the random forest regression creates an ensemble of decision trees. Each tree is built using a random subset of features and training data. Trees predict the target variable using their selected features and data. The final prediction is the average or weighted average of all the tree's predictions. So the model handles categorical, continuous, and missing data, which is something good, and it's less prone to overfitting due to the simple approach and random feature data selection. Using the random forest regressor, from scikit-learn with 250 estimators and a random state of 1. When we use that, it outperformed other regression algorithms. And probably this is because random forest combines multiple decision trees, reducing overfitting and improving prediction accuracy. It's good to know also that random forest regressor handles high dimensional data and captures nonlinear relationships between features and the target variable. And therefore, we expected, a good performance in our prediction task here. The second algorithm we used was the decision tree regression, and that predicts continuous numerical values. It recursively partitions data based on feature values until each subset has similar data points. Predictions are made by traversing the tree based on new data point features, reaching the leaf node with a predicted value. The main advantage here of decision tree include handling numerical and categorical data and human interpretability. However, it can overfit and be very sensitive to noise. So we use the decision tree regressor from scikit-learn with a maximum depth of 15 and random state 0. It performs slightly worse than the random forest regressor, as single trees are prone to overfitting and may not generalize well on new data. Increasing maximum depth can lead to overfitting and poor test performance. And probably that's why we got that result. Training many trees showed little gain in this case. Further research could explore this, but for our purpose, the random forest so far regressor outperformed the decision tree regressor. We used also the support vector regression, which is a very popular regression algorithm that is derived from support vector machines that is used for classification. So the support vector regression finds a high-dimensional hyperplane that captures the target variable's variance under a specified error threshold. It suits more small data sets and handles non-linearly separable data with kernel functions. We used the scikit-learn support vector regressor with a linear kernel, degree 4, and a regularization parameter of 1. And that was, we used that based on other promising previous research, those specific parameters. The Bayesian ridge regression, it estimates parameters using Bayesian statistics in linear regression. It incorporates prior information on parameter distribution to prevent overfitting and enhance prediction accuracy. So we used the scikit-learn's Bayesian ridge regressor, which estimates a a probabilistic model for regression. It assumes a spherical Gaussian prior for the coefficient, capturing prediction uncertainty and improving overall accuracy. And we're going to see all the results at the with numbers at the end. The next one was linear regression, and linear regression predicts the relationship between a dependent variable and one or more independent variables. It assumes a linear relationship and estimates coefficients to best fit the data. So linear regression is simple. And the scikit-learn provides an ordinary least square linear regressor that minimizes the residual sum of squares between observed and predicted targets in the weather dataset. It, as I said, it assumes a linear relationship and it estimates the coefficient using the least square method. Also, we're going to show the numbers of the results in a couple of slides. We also tried to use the neural network multilayer perceptron regression, or the MLP. And it is a layered artificial neural network that models input-output relationships. The good thing is that it can handle complex and nonlinear relationships. So we implemented the scikit-learn's MLP with a 200 by 200 hidden layer size, using the TAN activation, Adam solver, and adaptive learning rate. Convolutional neural network is also something that are widely used in image and signal processing. We used it here, a variant from it, the convolutional neural network with neural network, we call it the neuro-CNN layers, combines the benefit of the CNNs and the MLPs. So the neuro-CNNs use convolutional layers to extract features and fully connected layers for further processing. Our CNN architecture consists of 3 convolutional layers, 1 dense layer and 1 output layer. The input size is 15 by 1, representing 15 different features. So here we can see that we have the input layer size 15 by 1, convolutional layer 1 with 6 filters, kernel size of 5, and output is shape of 11 by 1. And then you move on to the convolutional layer 2 with 6 filters also as well, and kernel size of 5, but the output shape is 7 by 1. The convolutional layer 3 is 6 filters, kernel size 5, but the output shape is 3 by 1. And then we flatten layer, which converts the last convolutional layer output to a one-dimensional vector, as we see here. So the dense layer here includes 12 neurons. The output layer includes 1 neuron without activation for regression tasks, predicting continuous values accurately. So the main findings, to build the CNN, we experimented with different network architectures and obtained the following insights. Number 1, adding pooling layer resulted in worse performance. This is because pooling layers discard valuable information, which can lead to prediction errors, especially when working with time-stamped data. Here, this figure here shows that using 3 convolutional layers leads to better results than using only 1 convolutional layer. Therefore, adding more convolutional layers can increase the accuracy. We also experimented with different numbers of filters, like 256 versus 6 filters in small instance, like 1,000 instances. And also we did the same thing for large data, like in the when we used all the data, which is the 68,000 instances. Increasing the number of filters led to better accuracy for small data. But on the other hand, working with many filters was slightly better than using a small number of filters when we used all the data. Therefore, when dealing with large data, using a small number of filters can avoid overfitting. Also here, this figure shows that the accuracy improved when increasing the data size with a few filters. And based on these findings, we constructed our CNN architecture. Now, to optimize the performance of our regressors, we utilized hyperparameter tuning. Two techniques were used: the grid search cross-validation and random grid search cross-validation. For the SVR, we applied grid search to determine the best set of hyperparameters that maximizes the score of the left-out data. A grid was built with all possible combinations of the SVR kernels, and the best set of hyperparameters for the SVR was by using the C equal to 10 with a linear kernel. And due to time-consuming nature of that grid search, we used only a sample of 1,000 data instances. So we're not able to use here the whole data. We applied also in the second figure here, we applied a random grid search for the random forest regressor to determine the best number of estimators. The range of estimators was set from 200 to 800 with a step of 10. We tried a random grid search on the whole and sampled data. The best number of estimators for the random forest applied on the sampled data, and it varied between 200, 333, 600, 400, and 800. However, the best number of estimators for random forest applied on the whole data was always at 800. So when we applied it at the whole data, it was at 800. The primary difference between these two techniques is that the grid search we define the hyperparameter combinations and train the model on all of them. Whereas in random grid search cross-validation, the model selects hyperparameter combinations randomly. So as a result, random grid search cross-validation takes less time than the grid search approach. So in order to evaluate the performance of regression models, two popular metrics for continuous variables are the mean absolute error and the root mean square error were used. Also, we used the R-squared, and that's a metric to analyze the performance of different regression models also was used. So a good regression model should have a high R-square, a low mean absolute error, and a low root mean square error. So in this study, we used all three metrics to analyze the performance of 6 regression models. And as we can see here, these are the regression models that we used. So we applied the above regression models to the whole data set and also to a sample of 1,000 instances. So each model was run 5 times and the average of the runs was taken. Here, this figure shows the matrix for all 6 models, including the results of hyperparameter tuning for SVR and RF, the random forest. So as shown here, when applied to the whole data set, the random forest regression model performed the best. Perform here the best with an R-square of approximately 0.996. The mean absolute error was 11. The root mean square was 17.5. In comparison to the CNN that came in next with an R-square of 0.995 and a mean absolute error of 14 and a root mean square error of 21. We believe that CNN model can have better accuracy by applying more layers and choosing the best number of filters. When applied to a small data set, CNN performed the worst with an R-square of 0.445. Additionally, hyperparameter tuning of random forest and SVR increased the accuracy of both models. Specifically, hyperparameter tuning of the random forest with 250 estimators increased the R-square to 0.992 and decreased the mean absolute error to 10 0.3 and the root mean square error to 80. Similarly, the hyperparameter tuning of the SVR with a linear kernel and C equal to 10 increased the R squared to 0.988. Hyperparameter tuning of the random forest regression model for the whole data set increased the performance with an R square of 0.996. So this is a table that shows the conclusion here, and we can see here for the random forest performing the best based on the matrix that we used, followed by the CNN. So the study applied various regression algorithms to determine the optimal model for predicting solar radiation. And as a conclusion, the findings indicate that random forest regression yielded the most accurate predictions. The CNN ranked next with a difference of approximately 0.16 compared to the neural network MLP. However, improving the CNN architecture by testing different numbers of layers and filters could enhance its accuracy. The performance of the SVR improved by 1.6 after hyperparameter tuning, while adjusting the number of estimators for the random forest regressor resulted in a slight decrease in performance. And this decrease could be attributed to overfitting, as the tuning was conducted on the training data set. So for future work, we plan to conduct a comprehensive study on weather forecasting, which includes error analysis and a thorough comparison of predicted values for solar radiation against actual solar radiation. Such a complete analysis will benefit the field mainly if we provide detailed descriptions of the measures taken to minimize the errors associated with weather forecasts. Thank you for watching.